Welcome to this class. Our today's topic is the magnetic force between two parallel conductors which carry currents. There are two concepts which we will use here to derive the relation. The first concept is that if there is a conductor carrying a steady current I through it, then at a distance r away from it, there is a magnetic field produced. That magnetic field we can derive expression by using Ampere's circuital law, comes out to be mu 0 I divided by 2 pi r. Here mu 0 is permeability of free space, which means that medium surrounding the conductor is vacuum or free space, and I is steady current passing through the given conductor. R is distance of point P where we are observing the magnetic field. Now, the second concept which we will be using is that whenever we produce current through a conductor and place the current carrying conductor in a magnetic field, say this is a conductor carrying current I, and we have placed it in a magnetic field such that the magnetic field is perpendicular to the plane containing the conductor, and this magnetic field is a uniform field B. The force experienced by length L of this conductor, if the conductor has length L, would be given by BIL sine 90 degree. This angle theta is angle subtended between direction of current, or we can also treat it as direction of the length element here, and magnetic field B. In the present case, I have placed conductor in a transverse magnetic field so that the theta or angle subtended between direction of the length element or current element and magnetic field is 90 degree. So this force would be BIL. I call this as relation 1, I call this as relation 2, and we will be going to the concept now. The concept is like this, that if we think of the first conductor carrying a current I1, so there are two conductors, one is carrying a current I1, it's a steady current. Parallel to it, there is another conductor carrying current I2, the separation between them is R. Then how do they experience force with respect to each other? I demonstrate the situation with the help of a very simple idea which looks like this. Here, what I try to show is that if I have a conductor carrying current I1 through it, the current is upwards, there will be a magnetic field which will be produced. The surrounding line, which is one of the magnetic lines of force, is that if I trace a magnetic line at distance r, r is radius of this cylinder, so if I trace a magnetic line at distance r, it will be like this. How I found the direction of magnetic field? I use my right hand rule, put thumb in the direction of current, then curling fingers, they give the direction of magnetic lines. If I look at the situation from top, I find a current coming towards me at the center, and then there is a magnetic line of force surrounding that point, and that magnetic line of force in the present situation is anti-clockwise. Now this view I can trace on the whiteboard like this, that if this dot represents a current I coming towards me, then here is the magnetic line of force which will be a circle surrounding this point. Point is at the center, which is axis of the circle, and this current, say, is I1. This is the magnetic field. Assume that the distance between this is R. Now, these magnetic lines of force are everywhere. Like, if I make the cylinder, there is a magnetic line of force here, there is a magnetic line of force here, there is a magnetic force. They are all along the length of the conductor. Now, this direction of magnetic field at a particular point will be given by tangent drawn at this point. Like, if I want to find direction of magnetic field here, I draw a tangent here. I want to find direction of magnetic field here, I draw a tangent here. This tangent in the space will be represented by a line like this, or like this. So once I see the magnetic line being traced in the anti-clockwise direction. At this point, the magnetic lines are like this. And if I go on the diametrically opposite point, the magnetic lines are like this. Very clear from this diagram. Now, the strength of magnetic field at this distance r is given by equation number 1. So if I say that I1 is the current passing through the conductor 1, what would be magnetic field at distance r away from it will be given by mu 0 I1 divided by 2 pi r. Now imagine that at this point where all magnetic lines are going towards the observer, they are going away from me, I bring in another conductor, and that conductor is carrying a current I2. So here is the second conductor. Now this conductor, which is carrying current I2, finds itself soaked in the magnetic lines of the first conductor. तो यहाँ पर आप देखेंगे कि इस पर यहाँ पर भी एक मैग्नेटिक लाइन, यहाँ पर भी एक मैग्नेटिक लाइन, यहाँ पर भी एक मैग्नेटिक लाइन एक्ट कर रही है. तो ये सिचुएशन बिल्कुल ऐसी हो जाती है that you have a conductor carrying a current, say I2, और ये जो current है I2, this current I2 is current being carried by a conductor which is placed in a magnetic field produced by the first conductor. और वो magnetic field ये है which I could call as B1. Now if you go to the second equation tells you that force experienced by this conductor, second conductor, would be given as force experienced by the second conductor due to the current in the first conductor would be given by B. Who is B? B is this B1 multiplied by, who is this I? I is the current in the second conductor, which I call as I2 multiplied by length of the second conductor, which is L, so that would be the equation second. Now in this equation, these two, which I call as 3 and 4, if I substitute B1 equal to mu 0 I1 by 2 pi r, so I have F. Now this F is the force experienced by the second conductor due to the current in the first conductor would be mu 0 I1 divided by 2 pi r multiplied by, तो मैंने B1 को replace कर दिया, I2 and L remain as such. Or I can say that F by L is equal to mu 0 I1 divided by I2 divided by 2 pi. ये जो expression है, this expression tells us that how much is the force experienced by the second conductor due to first conductor per unit length, because F by L represents force per unit length. So my answer is that force experienced per unit length by second conductor. Second conductor is conductor carrying current I2. Second conductor would be equal to mu 0 I1 I2 divided by 2 pi r. So this is not now force, it is actually force per unit length. I denote it by small f because dimensionally its dimensional formula will be that of force divided by length. And this expression becomes now the expression for force exerted by a current carrying conductor in presence of another current carrying conductor which is parallel to it. The term parallel becomes significant because everywhere this distance must remain r. आधे का distance r ही रहना चाहिए. And the force acting per unit length will have dimensions of Newton per meter. Now what happens that if I think of the converse way, that the second conductor is actually producing a magnetic field and first conductor is soaked in that magnetic field, still the answer will remain same. The answer will not change. Now as we see that if we interchange the two conductors, the force of interaction between them will not change. So I can say that force experienced by first conductor due to second is equal and opposite to the force experienced by the second conductor due to first. This is a usual definition for a mutual force. That means the force between these two parallel current carrying conductors is a mutual force. About the direction of this force, we don't devise a new rule. We use the same idea as we use in case of the magnetic field due to or force experienced by a conductor in the magnetic field. We called it as Fleming's left-hand rule. Now what was Fleming's left-hand rule? The Fleming's left-hand rule said, so we have Fleming's left-hand rule. It says that if there is a conductor placed carrying current I, S for second finger, S for speed, first finger for magnetic field, thumb for thrust, then putting the first finger in direction of magnetic field, second finger in direction of conventional current, thumb gives the direction of magnetic field. Thumb gives the direction of force experienced by the conductor. So in this case, if I see that the magnetic lines of force which are produced by the first conductor, those magnetic lines are like this, as I showed earlier, that here the second conductor is finding magnetic field perpendicular in this manner, perpendicular. Now this magnetic field, which is perpendicular to the magnetic field, gives us a force F equal to PIL, and the direction of that force will be found by Fleming's left-hand rule. So I put my finger, first finger, in the direction of magnetic lines of force. These are actually the magnetic lines of force representing the magnetic field of the first conductor. Then I put my finger in the direction of current I2. The thumb gives direction of force acting on the second conductor. So in that manner, the direction of force acting on the second conductor is towards the first conductor. And we say that when two conductors are carrying two currents parallel to each other, I1 and I2, they attract each other. So if the currents are parallel to each other, there is attraction. If you reverse one of these currents, either I1 or I2, there will be a repulsion. That means if the two currents become anti-parallel, these two anti-parallel currents will produce repulsion among the two conductors. So this comes out to be a very simple rule that if currents are parallel to each other in the same direction, parallel to each other, there will be attraction. If the currents are opposite to each other, one is upwards, other is downwards, or the vice versa, there will be a repulsion between the two conductors. The basis of this rule is again Fleming's left-hand rule. So for magnitude, we have this, the force acting per unit length of conductor. For direction, we have to remember these two ideas. Now, this equation is also a basis for definition of the SI unit of current. Current is one of the fundamental quantities in physics, and this basic quantity has the unit, its SI unit is 1 ampere. 1 ampere. How do we define 1 ampere? When I say that force acting per unit length is equal to mu 0 I1 into I2 divided by 2 pi r, we can substitute value of I1 equal to 1 ampere, I2 equal to 1 ampere, R equal, if I substitute I1 equal to 1 ampere, I2 equal to 1 ampere, R equal to 1 meter, then force experienced per unit length by a conductor due to the other conductor would be equal to, the value of mu 0 is 4 pi into 10 raised power minus 7 multiplied by 1 divided by 2 pi into 1. So pi and pi gets cancelled, 2 and 4 gets cancelled, we get 2 into 10 raised power minus 7 Newton per meter. That way, we have a definition for 1 ampere. A current of 1 ampere is said to be flowing through two conductors each if they produce among themselves a force of attraction of 2 into 10 raised power minus 7 Newton per meter when placed in vacuum at a distance of 1 meter. Again I repeat that a current of 1 ampere each is said to be flowing through two conductors which are parallel, straight and infinitely long, placed in vacuum such that they are placed at a distance of 1 meter with respect to each other and produce an attraction of 2 into 10 raised power minus 7 Newton per meter. This becomes the basis of the definition of 1 ampere, which is one of the SI units, and it is the basic quantity. Current is a basic quantity, and the definition of 1 ampere is based on this concept. Thank you.